This is your OFDM transmitter and receiver, okay, using MATLAB, your fifth experiment. And as you all know, OFDM is nothing but your orthogonal frequency division multiplexing. So which means if it's a dot product, okay, the orthogonality property is actually embedded, okay, and the dot product should actually give us a 0. Fine. And in order to stop the carrier overlap, okay, so this technique is used, and ortho, okay, many carrier frequencies, so which means about eight carrier frequencies are there, okay, and hence the name ortho. Just a moment. Okay, so we have about eight carrier frequencies here, and hence the name ortho. The channel is actually divided, okay, for use of many frequencies, and this is about your block diagram. Okay, so just have a look at it, and you can see that the modulation is done and serial to parallel conversion is done. Okay, then IFFT process, then we will be inserting a cyclic prefix. After inserting the cyclic prefix, then parallel to serial conversion is done. Then it is actually converted from the digital to analog, okay, conversion. Then it is sent into the channel. A small noise is also introduced by default, okay, because we cannot have a noiseless communication. Then the reverse process of whatever we saw with the transmitter, okay, you will have a digital analog to digital conversion, so which means this transmission that's happening, okay, in the channel will be in the form of analog, okay. And then rest all is your serial to parallel, then your the cyclic prefix, okay, it's just like a key, whatever information that we have sent in, okay, so that will be used as a key, and we will be removing the cyclic prefix. Then IFFT will be given as FFT. Then here serial to parallel, here will be parallel to serial, and then it is sent to demodulation, right? So just have a look at these waveforms, okay, and try to make a note of it. So if you can see this waveforms here, okay, data coded in frequency domain. I hope it's visible, or do you want me to still zoom in, students? Is it fine? And then once it reaches to the next level, okay, which is the IAFFT, okay, all these are spreaded, okay. Then it goes into your transmit. Then when it's in the received mode, okay, the reverse happens, and we will again try and combine these signals just like how it was previously, and we can decode each subcarrier, okay. So this is the basic technique involved in our OFDM technique. Okay, so which means your transmitter and receiver, if you start writing the code, okay, it's almost going to be the same, and just that the reverse of the process happens. And as you all know, CP is your cyclic prefix. Okay, then there are guard bands, okay, which are actually employed as inserting bits, okay, because it's in the form of a digital mode. Okay, so we will be using the cyclic prefix. And IFFT, I think all of you know, okay, is your inverse fast Fourier transform, and your FFT is your fast Fourier transform. Okay. Uh, then the other information that you'll have to know is with the serial to parallel conversion, okay, which means a reshape command is given. Okay, so if you can see, the reshape is the command which is used in your programming. So we will get into it in a moment. So here this technique is used for radio transmission and reception in LTE. Okay, basically your 4G signals carries out the same functions as any other multiple access technique by allowing the BS, okay, the base station to communicate with several mobiles at the same time. Okay, so this is like a broadcasting information, a powerful way to minimize the problems of fading and intersymbol interference. So fading is one such thing where there is a degradation in your signal as the signal passes through. Okay, so that can be nullified with the help of this technique. And some of the examples that are used is your WiMAX. Of course, it was not that popular, and then eventually it died out. And then your IEEE 802.11. Can someone tell me what is this IEEE 802.11?
Wi-Fi.
Yes, exactly. So this is your Wi-Fi. You have A, G, N. You have AC. Okay, AC version also. Right. WiMAX didn't actually become that famous, as I was mentioning. Okay. Then with regards to your digital television, okay, and radio broadcasting. Fine. Now, the other thing that you'll have to remember here is how the transmitter works. Okay, how the symbols are taken, and of course, you would be learning about this in detail in your theory. Have you all come across these concepts in your theory as of now? Have they covered this? Have you reached this concept?
Yes, sir.
Yeah. Okay. Okay. So, so the other thing that you will all have to know is your information as to how it gets divided. Okay, if you give it in serial to parallel conversion. Okay, let's say your R into C, rows into columns, right? 1 cross 64 will be actually reshaped into 16 is to 4. Okay, so 16 is to 4, yes. So that will actually reshape, and it can convert, okay, the values from serial to parallel. So this divides the information into several parallel substreams. Okay. So ultimately, we are looking at broadcasting information in a more parallel way. Okay, rather than having the communication to be in serial. Okay, so that is why you actually see here, just for the transmission we are using this. This we are inserting CP, okay, and then we are using the parallel to serial converter just for the conversion process, and then we send it across, okay. And once this is done, okay, we will have one more block here, which is serial to parallel converter, and then from here on, it all happens in parallel. Okay, so you can say that this conversion, okay, analog to digital conversion alone, okay, we take bit by bit because we do not want to lose any data. Okay, we do not want to lose any data. Serial bit by bit is taken. Okay, right. So the next thing that we'll be looking at is this sends each substream on a different frequency, okay, which is subcarrier. So that is the specialty. And your frequency, okay, your each subcarrier can use an unique frequency. If the total data rate stays the same, then the data rate on each subcarrier is less than before, so the symbol duration will be longer, which is very obvious, right? Then this reduces the amount of ISI, which is nothing but your inter-symbol interference. So many times what we do is we we use guard bands, okay, guard bands in between the signals, so that there is a kind of a delay between one signal and the other, and this guard band is like a sandwich, okay, that acts between signal 1 and 2, so that these two signals are not you know uh, having these distortions. Fine. So here you can see that there is about 1 microsecond delay between each race, okay, and there is about 2.5 microsecond symbol duration. So we can choose as to how much bit rate that we want to, based on our frequency. Right. Next, the symbols on first array for subcarriers 100 kbps per subcarrier. Then symbols on second ray, okay, another 4 subcarriers are taken, and 100 kbps per subcarrier. So frequency 1, 2, 3, 4. So at different frequencies, we can actually transmit these subcarriers. Remember, I spoke about 1 is to 64 and 16 is to 4, right? The serial to parallel conversion. Then we use something called CP start. Okay, in your code, you should be able to see that. Let me just check here. You will have reshape. See, this reshape that I was talking to you about will actually help in serial to parallel conversion. So I will have subcarrier 1, 2, 3, 4. Okay, and this will be taking the matrix value. Okay, the matrix value 1, 2, 3, and 4. And the next is all about your subplot. Okay, and all those stuff. Right. Okay, and we are taking here n is equal to 256. Okay, this is nothing but your number of bits that we are considering that we are going to pass through. Okay, and the number of data bits will be 64 because it's number of bits per channel. Okay, and that is extended to about 128. Because if I can divide this, okay, with 4, because we have f1, f2, f3, f4, right? So m is equal to 4 will be the number of subcarrier channels, right? Then you can say that each block will be about 16, right? Then I think you can remember that your floor, okay, is about CP length. Okay, the cyclic prefix length will be floor 0.1 into block size. So block size here that we have given is 16, right? Okay, so similarly, this can be taken and you can actually plot what you want across your x-axis and y-axis, right? Then it is just as per your block diagram here. Okay, whatever you see here, one by one. Okay, so the same process you will be writing different blocks of codes here. So this one is just your initiation, which means analyzing how much of bits, how much of block, or what is your prefix length, okay, and with how much you're going to divide, what is your block size, all these things, right? So the first one that you'll be looking into here is with the transmitter, okay. So as I told you, transmitter, here also you will be giving data and naming your figure and all those things, right? Uh, then you'll be performing your BPSK modulation on the input source, okay, wherein you'll be naming it as PSK modulation. And these are again, given as I mentioned as your subcarriers, reshaping and subcarriers. Then your IFFT operation happens, okay. So basically, it's all about, most of them remains the same. The command and all remains the same. Just the thing is, you'll have to rename them as 1, 2, 3, and 4, right? And it's all same. Then you'll be adding a cyclic prefix here. Okay, just make sure that you calculate what is CP length. Okay, CP length was here initially. Some of you might forget to do this here. Okay, so CP length should be calculated, and then that can be actually called here, and it can be utilized. Then we'll be adding a cyclic prefix. Okay, and appending values to the subcarriers, making a subplot of each frequencies f1, f2, f3, and f4. And the final thing is, we are converting them to serial form, okay, because we have to just transmit it, right? And so whatever signals that you have transmitted, you should be able to see the same signals, across your uh, receiver, right? And then number of data bits is going to be 64 and m is equal to 4. Yes, we have seen that. Now for your subcarrier 1, okay, this is going to be your data, and you should be able to see the same data, okay, at your receiver end, okay. So all this is going to get generated. Your real and imaginary values are going to be generated. Okay, and you should be able to see these values at your receiver end. Okay. Uh, One more thing that I want to mention is about for adding two matrix, okay, combining, we'll be using something called vertical concatenation, okay, VertCat, VERTCAT. Okay, VertCat concept is also employed here, and you'll be seeing that, in your coding. Then cyclic prefix, yes, this is to take the last row from the column, right? So the last row is taken, and the append prefix uh, from each column, okay, we are going to take about 1 bit. The subcarriers are all orthogonal to each other, hence overlapping is possible because they are, at a different frequency, right, altogether. So that shouldn't be a problem at all. And in OFDM technique, okay, technique, it can be reduced, or we can see that our ISI is reduced altogether, and the bandwidth utilization is less. Okay, so this can be employed in BPSK, QPSK. Frequency to time domain is done in IFFT. That is one more important thing that is to be considered. Okay, and yeah, this is what I wanted to show you. This is going to be your original data, okay, and your modulation, the subcarriers, okay, the divisions that happens F1, F2, F3, F4, okay, and the IFFT operation that happens on them, okay, and the orthogonality property, okay, this is like seeing from the front view, okay, and the OFDM signal here, and at the receiver also you should be able to see the same sort, okay, where it is going to convert it back uh, to the form that we just saw. Okay, so the subcarriers, yes, so this is going to be the values received at your receiver. Of course, the values you can even look for a smaller block size, and you can compute values and accordingly see the graphs. Then the other thing is in cyclic prefix, the tail of the message is placed at the start. I think all of you know this. So that if there is a delay, the cyclic prefix section can be neglected, and hence ISI can be avoided. So this is also another thing that you can keep in mind. Uh, Next, one more command that I want to talk about is rand ser. Okay. So this is our general format where this generates a random matrix m cross n random matrix. Okay, and the alphabet can be either a row vector, okay, or a two-row matrix. Okay, then the other thing that you can see here is PSK mod. PSK mod. So the operation is it outputs the complex envelope of modulation of message signal using PSK. Then S2P, the serial to parallel converters, don't use semicolons there, okay, when you are actually doing this S2P, so that the output can be seen at every step. If you use that semicolon, then you wouldn't be able to see those conversions happening. Okay, right. So I will be actually sharing another information, okay, another link to you all, where you can have the detailed explanation also in another angle with respect to this experiment. Okay, so yeah, so this was about your OFDM. Okay, and this is how it is employed for your multiple uh, carriers. Okay, the operations that happens on your multiple subcarriers, and its importance of doing it. Okay, the reason for doing it is to have our ISI reduced. Okay, many other such benefits can happen with the help of these techniques.